Just making sure. Okay. See, I thought Ruben and Ryan said they would be here. But,
Okay, so thanks, Nat, for agreeing to give this very, I guess, pedagogical tutorial about numerical methods, stochastic series expansion. And I guess you'll also tell us some applications at the end, perhaps. I guess you'll pick this up to look at some problems of interest. So yeah, why don't you take it away?
yes, so thank you. So, right, so today I'm gonna be giving sort of an introduction to quantum Monte Carlo, and I guess there are many quantum Monte Carlo algorithms, but the one I'm going to be talking today is called the stochastic series expansion, which is used in like simulating spin systems. And the reference, which probably was sent out in the email, there are these two nice review papers, one by Roger Melko and one by the creator himself, Andrew Sandvik. So I think the one by Roger is a bit more introductory, and but for it's more pedagogical, but for a more complete discussion with more details, I recommend the second one, depending on how deep you want to go into it. So the goal of today is that we want to simulate sign problem-free spin Hamiltonians and obtain like expectation values of operators, or for example, the energy. And to do that, there are certain quantum Monte Carlo schemes that you can do for a class of Hamiltonians that might be interesting to condensed matter people, which are, for example, Ising model or Heisenberg. But these schemes can be sort of generalized to sort of, although they're like the most rudimentary one, they can be sort of generalized to more exotic sign-free problems if you want. And I'll give an example of what I've been using is to simulate a transition between trivial and SPT phase in 2+1D, which is sort of like hard to do numerically with, I guess, other methods. Right, so hopefully I'll get to mention that, but in any case, the main goal of today is to sort of give an introduction to the first part. So yeah, if there are any questions at any point, please let me know. And I'd rather spend time explaining if something is not clear. Okay. So to begin, so suppose we have a Hamiltonian that we want to simulate, and here I'm going to be in finite temperature. So you can write the partition function as such, and the trick of this stochastic series expansion is to sort of expand this out to rewrite this exponential as an infinite sum. And so for each, after writing this, you might have a bunch of terms in your Hamiltonian. So I'm going to write my Hamiltonian as minus the sum of individual terms. For example, if this is a Heisenberg chain, then I can write A as locating each bond in my lattice, and then H can be this S dot S term. And so this will just be summing over all such individual terms in the Hamiltonian. Now, if I plug this sum into the product minus H to the N here, then this, I can just, when I expand this out, this just become sum over all the terms of the different possible H's, where this, when I take this trace here, I'm just taking all the possible HAs that I can insert here, and I will be summing over all such configuration. So I'm going to call such configuration an operator string. So what I mean here is that S is just some label from 1 to n, and for each number index from 1 to n, I'm just labeling like A1, A2. It might be repeating, but you're just, by summing over this operator string, I'm just summing over all possible insertions that I can put into the Hamiltonian. And then if we do such, one thing is actually to calculate observables. So one thing you can do is to calculate the energy, you just do the usual formula to pull down the energy from the partition function. And once you do that, you'll find that if you take the derivative with respect to beta, like as such, you'll pull down an n over beta from this exponential in the sum. So the energy can actually just be evaluated as the expectation value of n with a minus n divided by beta, where n is the number of operators inserted in your operators string. So if you sample over all configurations that have that vary in the number of n, the expectation of value of n can tell you the energy of the ground state of your the energy of your Hamiltonian at finite temperature. And moreover, for other expectation values, if they're a diagonal, then they are also easy to evaluate, because if they're diagonal in this basis, then you can just insert this when you insert this O into the Hamiltonian when you do the sum, and then when you take the trace, this is just a number. So this is easy to evaluate when you're sampling this partition function. Okay.
So Nat, just to make sure I got,
yeah.
when you said diagonal, you mean these alphas are in some particular basis, like SC?
Yes. Yeah, for example, let me choose alphas to be spin up or spin down. And if as long as O is say some poly Z or something diagonal, then when you sample this is easy to do.
Right.
Right. When you so going back, yes.
Yeah, do I need to make a truncation on n?
Yeah, I will get to that soon. So right now n is going from 0 to infinity, but a few slides I'll show how to truncate it. But the truncation is not an approximation, actually. You can do it exactly, which is the nice part of this. So usually if you simulate your Hamiltonian by trotterizing, then by trotterizing you're doing some approximation. But it turns out by doing it this way, you actually don't have to approximate. Yeah, I'll get to that in a moment. Right. So going back to the partition function. So the partition function right now, I'm just writing as a trace over all insertions of terms in the Hamiltonian. And I'm summing over all such possible configurations. I'm calling this operator string. And right, sorry, maybe I did this in the wrong order, but you can insert a complete set of basis states, and this basis states I'm just choosing, say, to be, say, spin up, spin down. And now if as long as your Hamiltonian here has have matrix elements that are positive in this basis, then we can just treat this as a classical StatMech problem, because these are just then weights of a classical partition function, and then you can sample it. So right now, as it's written right here, what I have to sample is over the various lengths of n when I do the trace, how many operators I insert, and Sn, which is the string, what are all the possible operators I insert, and then finally alpha, which are the spin configurations, for example, of my system. So as it's written right now, I have to sample over these, and n can go from 0 to infinity. So as right now, it's not very practical. But now what you can, an observation is that in practice, when you sample this, configurations with large n are very unlikely. So in practice, when you simulate the system, n will never fluctuate beyond a certain value. We call it big M. So what you can do is, instead of sampling over the various n, you can fix a string length m. So that means I'm only inserting big M number of operators, and I'm just fixing that. And then instead, I vary, instead of allowing only terms in the Hamiltonian, I allow those in addition to the identity operator, and that will allow so right now I want my string to also allow identity operators. And now I can just do a sample over a fixed string length, and the number of operators that I insert will never, in practice, will never go beyond this big M. So now I am just sampling over. So here, this is Sn was sampling over terms in the Hamiltonian HA, but now Sm here is sampling over HA, and also I can insert the identity. Right. And then now what I mean by little n is that little n is just the number of non-zero, non-identity operators that I insert to my string. Okay. Does this part make sense?
How do you choose M?
Oh, right. So in practice, what you have to do is you have to you can start with a small m, and in your simulation you would have you would go between different configurations, and that would fluctuate n, and whenever n goes to some fraction of big M, then you just increase big M, and then you keep doing that until you find that big M doesn't increase anymore. And then so sort of like, suppose I plot like n as I simulate it, it is sort of like rise and then maybe like sort of die out. Sorry, this is big M. So I can sort of like increase every time like little n comes too close to big M. So then after a while, your size will be limited, and then n will sort of only fluctuate like at some fraction of big M, and then you'll be safe.
I'm a bit confused by your graphic. Do you want M to be on the other axis and then check the average number of non-zero entries on the y-axis or something? Or why would it? Because M is the thing you choose, right? So why would that plateau? That's a bit confusing.
Sorry, could you add?
So I'm confused by the graph you just drew. Don't you want capital M to be on the x-axis and then argue that the y-axis, which is, you know, when you measure how much of the string is used or something, and then above a certain threshold value of capital M, it's not using any of the extra string length? Maybe I should say differently. I'm confused because capital M is the thing you choose, right?
Right. But you also can increase that. You don't need to fix.
It's just confusing.
Oh, sorry. This is the x-axis is sort of like configuration as you're sampling.
I see.
This is like sampling.
I see. Okay. Thanks. Actually, I had a related question. So you say practically, so it's not exact, it just do a very good approximation, or does it become exact for a large enough value of M? Right.
So if you sample long enough, then n, little n could go beyond big M. Yeah, but for the time with which you're sampling, this is the, well, I mean, you can't explore the whole, you don't plan to explore the whole configuration space anyway, so.
Okay, thanks.
So to the, right, to the extent that you're only sampling the space, it is good enough, yeah. Right, but yeah, compared to trauterization, you do introduce some error and some approximation, whereas here the error that could go wrong is just in the sampling itself, which, yeah.
A basic question.
Yeah.
How do you assign the probability for the strings?
I will also get to
mean,
that. Right now, I'm just.
Can you explain why n never fluctuates beyond a certain value m? I guess I don't get that statement.
Oh, well, when you sample, n will have some expectation value, right? And then it'll fluctuate with some sort of sigma. So, I mean, it is possible for n to go up here, but it's very unlikely. It can fluctuate beyond your value, but it's very unlikely, right?
And how is big M depending on the system size?
Right. So big M usually scales linearly with beta, inverse temperature. So if you go to lower temperature, then your M will be larger.
And linear in system size, I guess, right? In total number of cells.
Let's see.
I would think it'd be independent of system size because it's just set by the convergence of the Taylor series for the exponential.
Yeah, I think it is independent.
But you have more terms in Hamiltonian somehow, but it does not affect it. Because that, like, the approximation is like, then I see what you're saying, but the exponential is of a bigger sum of terms, right, for bigger systems. So that could, maybe I'm.
Let's see, how does this work again? The runtime scales with system size, but I don't think the string length depends on system size. Yeah, sorry, yeah, let me think about it. But I don't think it depends on system size. Let me double check again, but I think it's correct that it, because when you're even though you have more terms to insert, you're only inserting like one at a time. You're not inserting like multiple operators at the same time.
And just to check that your last equation, is that exact identity, or it exact when M is large enough?
Yeah, I guess, sorry, maybe I exact in the sense, exact up to how, exact in practicality, sorry, maybe I shouldn't use the word exact, but in practicality, this is the same partition function. You can truncate this without much harm when M is large enough, big M is large enough.
Okay, thanks.
Okay, any other questions? So right now we're gonna, instead of sampling over all possible string lengths, I've truncated to a finite systems, finite string length. And now we just need to sample the strings, which consists of terms in the Hamiltonian or the identity, and then also spin configurations.
Nat, maybe you mentioned this, but N, the M, does it depend on temperature?
Yeah. So if it usually it scales linearly with inverse temperature beta.
Okay, makes sense. All right, thanks. Mm-hmm.
Okay, so now I'm going to talk about the update scheme. And so we're treating the partition function as a sum of weights, and the weight depends on some configuration X. And in this case, it's sort of our operator string and our spin configuration. And I'm gonna delay this updates scheme in a bit, but right now I just want to review how to get to different, what is the probability to go between two valid configurations, X and X prime. And one popular one is the Metropolis update. I just want to review that quickly. So given Z is a sum of weights, the weights here, you can just choose the probability update as the ratio of the two and then take the minimum. So you notice that when I take Wx prime over Wx and compare it to Wx over Wx prime, one of them will always be greater than 1. And so you just choose the one that to be greater, choose a probability in the case that you get some ratio that's greater than 1 to be 1. And then you'll find that the ratio of the probabilities are indeed just the ratio of the weights. So this satisfies detailed balance, so you can go from one configuration to the other by just calculating the ratio of the weights. Okay, and then in a bit, I'm going to talk about the updates, how to go between valid configurations. But first, this sort of depends on the Hamiltonian you want to study. So now I'm going to narrow it down a bit, and then I'll focus mainly on the transverse field Ising model. And that will, and then I'll introduce a particular algorithm for that. And so, right, and then let me note that there are different like algorithms you have to use if you are simulating different systems. For example, if you're doing Heisenberg, then it's sort of another scheme. But to give an example, I'll just focus on transverse field Ising for today. Okay, so I'm going to simulate a transverse field Ising model. This can be in any dimension, so I can put it on any lattice I want with arbitrary vertices and bonds. And the Hamiltonian would just be negative sum of your poly X on each vertex and ZZ term between for each edge. And for the purpose of being able to simulate it, we require H being greater or equal to 0. And J can be greater or less than 0, but for simplicity, let me just assume J is greater than 0. So now we won't be simulating this exact Hamiltonian. We'll be instead simulating another Hamiltonian, HQMC, and it's just related to the original Hamiltonian by some constant. But the constant here is just added so that, for example, for each Ising term, ZZ has eigenvalues +1 or -1, so that's sort of bad. So you can add 1 so that the eigenvalues of this term here is always either 2J or 0. And that allows us to treat this as classical weights. And for another thing that's been added to the Hamiltonian which will be useful for the update scheme is just this transverse field parameter H, and then this is just times the identity, and I'll mention why this is sort of useful. But anyway, this is just a constant, and it doesn't. You can always relate back to original Ising Hamiltonian. Okay.
It's a negative of H Ising, right? HQMC is negative H Ising.
Did I have a sign mistake here?
They both have minus ZZ, right? I think it's the same sign.
Correct.
Oh, it is the same sign. Okay.
If you look at it,
oh, it's just you shifted by constant.
Yeah, I have a minus. Yes, I have a minus in front of both, and I shift them by a constant H here and a constant J here. Right. So I'm labeling this as H for each site here, A, and then I'm and these are the three terms that I'm going to be pulling in and out of my operator string. So when I sample, I'm going to sample over possible configurations of these three operators inserted at various positions. So to give an example, let me show you what the configuration space looks like. So in this, I've drawn it sort of like as a space-time diagram. So alpha here are my spin configurations, and I'm just going to color it as white as spin up and blue as spin down. And let's say I have 6 sites. And this axis is sort of like the time axis, and I'm going to time evolve it big M steps. And in between, I'm going to insert various Hamiltonians. So my operator string is just a string of the different terms in the Hamiltonian that I can insert. And if it's the identity, I've just labeled this as -1, -1. I guess for this, this is just for the purpose of implementation on a computer, but for this purpose, you don't care about the notation. And there are 3 operators I can insert. It's H time identity, H time poly X, and this 2-body diagonal term. And so if you sort of try to draw it out, this is sort of what it looks like. So for example, here I start with this spin configuration. I evolve it 1 time step. There's no operator inserted, so everything looks the same. In the next time step, I insert a poly X at site 5. So I've noted that as a red square here. And after that, the spin sort of gets flipped. So now the down spin becomes the up spin. All the other sites are the same. I can also insert the identity times H, and that does nothing to the spin, etc. I can also insert this Ising, which I've written as a bar here. So it's sort of like a 2-body operator, and that doesn't flip any spin. And so if you just plug everything in, you get this whole sort of space-time configuration. And note that because we're taking the trace, this guy wraps around itself. Okay, so this is a valid configuration. And when I go through valid configurations, I just want to find, I want to sample through the operator string here and the spin configurations here. So I'm going to sample over, I'm going to go through different configurations of this and this. And the picture drawn here is just to see what it actually looks like. Okay. So to go between valid configurations, which is discussed in this paper here by Sandvik, there are 2 main updates that you can do to your state, and which guarantees that this would be ergodic. So you can go to any valid configuration from these updates. One is a local update called the diagonal update, and what it does is from an identity gate, you attempt to insert either H identity or this 2-body term. These are both diagonal terms in the Hamiltonian. Or if you run into one of these, you attempt to remove it. And the other one, which is a non-local update, which actually makes the simulation faster than that what you would do usually is from an h times identity, you would want to change it to h times poly x, which flips a spin. Okay, and I will go through these in order. So the first is the diagonal update. So what that does is, suppose what I can do is I go through each operator in my operator string that is sort of like each time step. And for example, in the first layer here, there's no operator inserted. So I could add either H identity or the two body diagonal gate with some, or this Ising gate with some probability. So for example, I go through this and I insert one of these here. That's a valid, so I've gone through another valid configuration. Now I move to the next step and I find a non-diagonal gate. In this case, it's poly X. So I just, I can't do anything about it. So I just move forward. And in the next step, I find a diagonal gate. So I attempt to move it. So there might be a probability of, there's a probability of removing this gate. Suppose it's successful, I sort of move it and I get rid of the operator. And so going through this to the whole string, I can sample through different diagonal, I can insert and remove different diagonal operators. Right, so note that here the spin configuration is completely the same because all of these operators I remove are diagonal, so I don't need to do anything to them. Right, now for each time step that you remove or insert, you need to calculate the ratio of the weights before and after so that you can calculate the probability. And so probably this is the most annoying slide in my presentation. Hope you're not too afraid of it. Let me try to break this down. So the partition function is written as like this, and I'm just basically treating this as a weight, and I'm just calculating the ratio of the weights before and after. So I'm going to consider the case where I start with a certain spin configuration without, a configuration without an operator insert. It's just identity, and I'm going to attempt to insert it. And so I need to calculate the ratio of the weights before and after. So before is identity, and it turns out I have to put a 1/n here just because the identity can sort of be placed at any location, for any site. So I have to normalize by 1/n. But everything else, the only thing that changes here is that I've inserted an operator. So the only change in the end is that everything else will cancel, and I only have the diagonal operator that I inserted divided by the identity operator, which is just 1 here. And this is just some weight you get from the calculation over here. So if you want to insert H identity, then the probability would just be this, because the expectation value of this operator is just H. And suppose you want to insert the Ising term, 1 plus ZZ, then the probability depends on whether the spins of your configuration are aligned or anti-aligned, because the eigenvalue of this is either 0 or 2, depending on that. So then the probability of inserting will just be 2j times that factor, or 0, depending on whether your spins are aligned or not. And so by detailed balance, if you want to remove either H times identity or Ising, then the probability is just sort of like the ratio of the weights is like you sum these two and then you invert it, and then you'll get this expression here. And the +1 here, in case you're wondering, is just because taking bookkeeping of how many operators I had before or after. Okay. Any questions about the diagonal update? Okay, so now let me move on to the non-diagonal update, which is also called the cluster update. So the next thing I want to do is, in the previous one, from identity, I've inserted diagonal operators, which are H0 and H2. Now what I want to do is, if I run into an H0, I want it to change it to an H1, which is poly X. So from H identity, I want to change to poly HX. But the problem is I cannot flip just one of them. For example, if I flipped only one of them here, I have a poly X here and I just remove it, then this sort of messes up the spin here because I have to also flip the spin. So the only way to make it consistent is that I have to remove two of these at the same time or insert two of these at the same time. So I can sort of label all the spins I have to also flip in the configuration here. And then when I do the update, I remove two of them at the same time. Okay, so I can go through between H identity to HX. But now let's consider a more interesting one. Suppose I want to flip these two. I want to remove these two. Then I would say, okay, I can flip all the spins here. But what happens if I just do that? If I just do that, when I flip these spins, actually, this configuration is not a valid configuration because H2 here depends on, you can only insert the Ising if the spins are aligned. So the probability of inserting such a state when the spins are not aligned is 0. So actually you cannot, this sort of move is not allowed between valid configurations. So the way to fix this is that instead you have to also flip this entire row of spins, which implies that you also have to add switch between H identity to HX. So you have to flip all these spins and change these two. And you can see that you also run into the next Ising operator. So by the same logic, you also have to flip everything here as well. So at the end of the day, you'll find that you are not flipping just one row, you're flipping an entire cluster of stuff. And that's why this is called a cluster update. So what you do is you identify this cluster, and within the cluster, which is shaded orange here, I flip all the spins. And in addition, I toggle between H identity and HX at all sites here. And in this case over here, note that I'm flipping, since this cluster went all the way around time, this endpoint here, that is the operator here, is sort of like at the endpoint of two clusters, the same cluster twice. So I actually don't need to flip it. Okay, right. So one property is that for each spin in this simulated spacetime, every spin always belongs uniquely to one cluster. So what you can do is that in this space here, you just pick a spin at random, and then you identify the cluster by what I've just shown, and then you update it to the other valid configuration. So you flip all the spins in the cluster, and at the endpoints, you toggle between H0 and H1 for all these endpoints of the cluster. And now the reason we introduce this operator here with coefficient H is that you can notice that when I flip between these clusters, the expectation value of H0 and H1 is it's just H. So the ratio of the weights is just 1. So I can always flip any cluster with probability 1, and that's the nice part about this algorithm. So you just identify some number of clusters, and then you attempt flip them. The flip is always accepted. So in practice, what people do is you don't want to sort of flip everything, otherwise you won't go anywhere in phase space. So in practice, people use a probability 1/2, so that you only sort of flip half of them, and that allows you to go as far as possible. Any question?
Maybe I just missed it. So you said every cluster can always be flipped to probability 1. Where is that statement coming from?
Right. So you can go through calculating the weights for each configuration, right? And let me go to the so it's a similar calculation to this, but you're treating this as a weight. And then for each operator here, you're calculating the expectation value for that operator inserted. But in the cluster update, you're just toggling between these two states, these two operators, and they both have expectation value H. So everything before and after just cancel. And so the ratio of the weights is just 1.
I see. And so related question, I think you explained this to me before, but maybe you can remind me and also tell others. But so on the one hand, detail balance tells you the probability is 1, but at the same time, you have the freedom to actually just make it a half.
Yes, you can actually make it whatever you want.
Can you explain that part? Why it doesn't matter what you choose?
Right. So like in practice, you only want to flip. If you flipped all the clusters, and if you flip all the clusters, you won't go very far in phase space. So you want to be as ergodic as possible. So by choosing this probability to a half, it just means that, okay, I flip a coin whether I want to flip this cluster or not. And if I choose to not flip it, then it's as if I never considered that cluster in the first place. So it's just like choosing clusters at random to flip. Yeah, you can think of it as flip a coin and choose which clusters you want to flip. Then calculate the weight. You find that the ratio, you can always accept such a flip. Then you flip it.
I see. It's interesting. And so detailed balance doesn't care if you ask the question of whether you can do it. Like it seems detailed balance is obeyed even if you neglect asking the question if you want to flip it. Right? That's what you're saying.
Right. Because you can go between any configuration you want at any point. Right. You can go through any configuration you want with some probability. Since you can always go through this, but you don't want to do all of them, so you just choose which ones you want to flip. So you just do that by choosing randomly. Right.
So just to see if I understand, right? So you're saying detailed balance just tells you if you specify 2 states, detailed balance tells you what the probability is, but you get to choose which 2 states, and that's what you're using essentially, which states you want.
Yeah.
Okay, thank you.
Okay, thank you. Any other questions about this chart? Yeah, and so I mean that's basically it for simulating Ising model. That's sort of the core algorithm. I guess I haven't talked about how to implement this efficiently on the computer. If you're interested, you can check out these references for more details. Also, I haven't mentioned how to simulate, say, the Heisenberg type model. There's another algorithm that does something similar where you do a non-local update, and in that case, instead of clusters, you flip something like loops. So it's the idea is sort of similar, but you can check it out if you're interested. Right. So I guess for the remaining time, I'm gonna extend this a bit, and then I'm gonna try to show you how you can use it to model transitions between SPT phases. So for example, you can consider from this Ising model, you can consider adding an SPT Hamiltonian. For example, in 1D, you can add this cluster state Hamiltonian. And it turns out that you can do a similar update as long as K is between -h and h. So what you do is you just change your a spin flip term into a 3-body term, which consists of you can sort of just pull out the x here, and then you'll get 1 plus k over h times this z on the 2 sides. Right, and then basically the algorithm is more or less the same, and the only caveat is that now when you're when you do the cluster update, you need to insert this 3-body operator instead of just the spin flip. And so what you have to be careful about is when you flip such a cluster, you have to check whether you have to calculate the probabilities carefully, because, for example, when I flip between these 2 states, you can see that when I flip the spin here, I'm flipping sort of the spin up to spin down here, and that changes the weight of this operator here. For example, it's 3-body, so there's a poly z over here, and this poly z might get flipped if you flip this cluster over here. So then you have to take care of calculating the weights before and after carefully. But that's basically it. You just need to take care of this probability, and everything else works the same as before. Okay. So
you need the condition that k over h is less than 1, right?
Yes. So in order for this to be positive, you need k to be between k over h to be between -1 and 1.
Have you explained why you need positivity in this talk yet, or did I miss it?
So that the weight is the expectation value of this is positive, so that you can treat it as a weight. Classical.
Right, even interpret as a probability, you're saying, right?
Yeah. I think it's the same condition as being stochastic, and because there's just a minus here. So instead of elements being minus, elements are plus here because it negated the Hamiltonian.
It's kind of interesting. The sign problem coincides with the transition, right?
Right. You have a problem right at the transition.
Which is not a coincidence, right? I think the SPT probably has like a no-go. I think Ryan also. Let's see. For 1D, I think you can actually the SPT is sign problem free, because you can simulate it as like z and xxx or something like that. For this case. So actually, I think it's fine. I see.
But
so there's no
but for the purpose of putting it in this sort of update scheme, yeah, sort of.
So maybe there's a no-go with translation symmetry or something.
Well,
or maybe I'm just...
there are 2 sites per unit cell here, though, so it's with translation is sort of.
Well, the symmetry is not okay, but the Hamiltonian is translation symmetry. Yeah. But okay.
Yeah.
Well, also, your Hamiltonian doesn't have the Z2 cos Z2, right? So. Because of the Ising. I mean, you have the other symmetry.
Right. If you add this term, yeah, then it won't have it. It still has a global Z2 and time reversal. Okay. Right. So this is how you can add SPTs in 1D and simulate them. And what I want to apply this to is an interesting SPT transition in 2D. And this is something I've been working on with Ryan, Ruben, and Ashwin. So instead of the cluster state in 1D, the SPT I'm interested is in the following. Instead of having 2 Z2 symmetries, it has 3 Z2 symmetries. And the model can be described as putting it on a triangular lattice and I can color my triangle lattice as blue, red, and green sites. And the symmetry is just a spin flip on either the blue sites, the green sites, or the red sites individually. And now the SPT, so I have a paramagnet here, but I also want to get an SPT, which is the following. The projector is an X decorated by a bunch of control Z gates between these two sites for these 6 sites surrounding the SPT. Right. So for those of you who this is a sort of type 3 SPT in 2D. But if I restrict to the diagonal Z2, so if I have a global Z2, this is in the same phase as the Levengood state. And so without the Ising term, this interpolation between paramagnet and SPT actually has been studied using quantum Monte Carlo by these guys here. And what they found is that they don't find a direct transition between trivial and SPT, but there is an intermediate ferromagnet state phase, which breaks all of the 3 Z2s. So unfortunately, they don't find a ferromagnet.
Am I the only one who cannot hear Nat?
I can't hear him either.
Nat, we cannot hear you. I don't know if Nat can hear us.
I think he's frozen. Right.
Right.
Actually, till he logs back on, isn't there some sign problem with simulating the double semi-on model?
Right, but I guess it's similar to your earlier comment, right? That we can simulate half of this model, and the other half actually is obtained by duality anyway. So by knowing half the phase diagram, you know the other half. So it's.
So getting to the brink where you're just just encountering the sign problem, that's okay. That doesn't.
Yeah, Nat has been doing that line as well. Yeah, that's possible.
So this Scafidi thing, they got only half the phase diagram, I guess. And
they noted that for some reason they could not do the halfway point. They could not do, and I think it's because from our perspective, we understand that this halfway point is an enhanced U1 symmetry, and I think they missed this. So probably their code got stuck because they were maybe initializing in the wrong U1 sector or something. That's my guess.
Okay, Nat is back.
In progress.
Hi.
Hi.
Sorry, somehow my laptop left, but my iPad is still there. Let me share again. You see me on the screen?
Yeah.
Okay. Right. Sorry, I missed the discussion just now. But
it was about sign problem, but that's fine. I think
okay.
We'll get back to that later, maybe.
Right. So the story is very similar to the 1D story I just said. So instead of having a ZXZ term, you instead have a ring term. So instead of having 2 Z's around it, you have a ring term like this. And then now your simulation in 2D is just flipping between H identity times H time a flip with some weights that depend on the configuration of all the 6 spins around it. So you can do a similar cluster update. So yeah, so
So the control Z, can you just remind us how those terms are working?
Right. So control Z is just if it's a +1, sorry, it's -1 if both say this spin and this spin is down, and otherwise it's up. So it's the diagonal gate. So then for 6 spin configurations here, you can just read this off as either +1 or -1.
I see.
Yeah. In the 1D case, that was ZZ on neighboring sites. Here it's just a more complicated diagonal operator. Okay. Right. So the expectation is actually that if you add an antiferromagnetic term J, then you can sort of leave the ferromagnetic phase, and there might be a direct transition between trivial and SPT. And so the way we determine transition is that we can calculate the Binder ratios for different system sizes. And for example, here I am plotting Binder ratio against the antiferromagnetic coupling. And as you increase J from 0, you find that there is a crossing over here. And so so you see that sort of there's a second order transition over here. And you can actually use that to plot the phase diagram. And also you can sort of plot the order parameter of this ferromagnet, and you can see that it also goes away somewhere around here. And so this is the result from numerics. And so we find that you can indeed leave ferromagnetic phase, and then there seems to be a sort of a direct transition between trivial and SPT over here. Yes. And let me mention, by the way, that you cannot simulate quantum Monte Carlo on this side, but we know that there's a duality relating trivial on SPT, and that's just the SPT entangler. So you just need to reflect your phase diagram over here on the left to get the result on the right.
Is there a similar trick as what you told me about in 1D with the XXX and ZZZ? I guess not, but just wanted to check in 2+1.
Yeah, I haven't, but in that case, you can just simulate it directly, right? If you're in that basis.
But you mean if you write it as XXX plus ZZZ, right? Yeah, so I agree. Yeah, so that's what I'm asking. Is there a similar trick?
Let's see.
I guess not, because I think people have proven that double semion you cannot get with sign problem free Hamiltonian. So that probably proves it's not possible, but I don't know.
Yeah, I think maybe Levin-Gu can be done sign problem free, but double semion has a problem. I'm not sure, but I know double semion there does have a problem, but it's not clear to me that Levin-Gu will have a problem.
So there's a loophole around this result that you could simulate the ungauged version, perhaps, with a sign problem free. That's known, or? It's interesting.
I remember vaguely discussing maybe with you guys or someone else about this, but I don't remember anymore.
Yeah, that would be interesting to know that. It's certainly possible that, the fluxes give you the sign problem, right? It's certainly possible that the SPT is sign problem free, but the gauged version is not. But of course, the best way is to actually have a model that you know is in that phase, right? And it has no sign problem.
Right. And that you say, you think or you know that for Z to SPT, it's like known or established that you can do it sign problem free?
You mean this Levin-Gu? Yeah, maybe I should not make a statement, but I thought there was nothing against that.
I see. Thanks.
Here, because the result from, say, Matt Hastings' paper is only for double semion. Right.
Well, these simulations are dying right on the brink, right? So that may be another sign. It's not a proof, of course, but
Which
you're not
simulation?
able to go into the SPT, right?
Well, but you could make the same comment in 1D, right? And if it's true, if you use XZX formulation, you cannot do the right-hand side, but then Nat pointed out that you have this, you can map it to XXX plus UZ, and then you can do it. So maybe there's a similar trick.
I see. Yeah.
Yeah,
maybe.
I just don't know whether.
Mhm.
Okay. And I guess the other thing I wanted to mention was that on actually at the midpoint between Trove and SPT, there is an exact U1 symmetry that is not there anywhere else. You might have heard it from my March meeting practice talk, but yeah, there is a certain U1 symmetry here, but we believe that after you go along this critical point, the U1 becomes spontaneously broken, and that's because the Z2 cube symmetry here has a mutual anomaly with the U1 symmetry that is that maybe I shouldn't say emergent, but that exists over here. And so that sort of motivates us to think that maybe there is a similar transition to the DQCP that happens in 2D, where usually on the nail face you have an SO3 symmetry breaking, and on the VBS you have some rotation symmetry breaking with this U1 in the continuum. But in this case, it seems like we have a U1 symmetry breaking, and this U1 can be actually written explicitly on the lattice, whereas this SO3 might emerge on the continuum, and here you might only have a Z2 square subgroup of it, which is symmetry breaking. And in case you're wondering, in case you're curious, the emergent U1 on this triangular lattice is given by a sum of ZZZ terms on a triangle where you weight the triangle. So up triangles has a plus sign and down triangles have a minus sign. So it's quite a weird U1 to think about, but it's an exact symmetry right at the critical point, and it anti-commutes with the symmetry. So these two have a mutual anomaly. So since we see a ferromagnetic phase here, and as we tune J up, it leaves the ferromagnetic phase, then we believe that this part here has a U1 symmetry breaking. And so we were also trying to probe that from our simulation. And what we realized is that in this, what we tried for fun is that this Hamiltonian here, an order parameter for the U1 is sorry, I should have written H0 minus SPT, because the U1 is actually, the Z2 subgroup of this U1 actually is the entangler between trivial and SPT. And so it H0 minus HSPT is anti-commutes with the U1. So it serves as a good order parameter. And you can, at the midpoint between trivial and SPT, you can obtain this exactly by taking the derivative of the energy with respect to this interpolating parameter alpha. And so we just did like the most basic thing, which is just take the derivative sort of like by hand numerically as you approach where I fix the right hand side to be 0.5, and then I increase the left hand side as you and then we find that at the critical point here there seems to be an order parameter coming up, and so we sort of expect that, okay, and the crossing point seems to be also at the same, roughly at the same point as the ferromagnetic order parameter going away too. So it seems that this point can be a deconfined critical point. Yeah, and I guess that's all I've prepared. So if there are any other questions, I'll be happy to take them.
So Nat, can you just go back one slide? I'm trying to remember whether you're saying this critical point is CP1 theory, non-compact CP1.
Right, I think.
You're saying it's same as the
maybe-
nail to VBS, like with the
Yeah, that would
U1.
be the conjecture, because we can sort of map the the symmetry sort of map to, you can sort of embed everything in this SO5.
Right.
So remind me, the Z2 cubed, can you embed that in the SO3? Or?
So you can embed two of them, and
Yeah.
and then the other one will be a charge conjugation of this U1, because it anti-commutes with the U1. So the diagonal one will anti-commute, and then that will be the charge conjugation.
And one other thing to mention that stabilizes it is that there's also the lattice symmetries, like 60-degree rotation, 120-degree rotation, and both around centers and around bonds. And those also map to something in the field theory. I forgot exactly, but I think it helped preventing certain anisotropies that help to stabilize the SO5, at least we think.
Yeah, I believe we have a cubic symmetry in this SO3. So it's not going to be like easy plane or anything like that.
Right.
Right. I remember when we started out this project, we were excited because it, gives like a sign problem free, DQCP. But then I guess there are a bunch of papers already doing that. But maybe there's still some extra. It's still an unusual kind of realization of it. So I think it's quite fun. But I don't know exactly.
Yeah. This embedding of symmetries, I think, is different. Having the U1, like instead of the C4 having the U1, that's certainly an advantage. Question is giving up the SO3 instead of for the Z2 cube. The question is how bad is that? But maybe it's not that bad. It's less bad than giving up the U1 for the C4. In terms of eliminating irrelevant, in terms of eliminating potentially irrelevant operators, so that they're just not there.
You mean just because you don't have to do with you don't have to deal with the monopoles?
Yeah, but you have some anisotropy, right, on the SO3 side. So that's the price you're paying, but maybe it's less severe than the C4 anisotropy.
Yeah, they will be like cubic operators in the scalars of some kind.
Maybe sixth order or something. Z1 squared, Z2 squared, well, what is the other one? The product of the ends or something.
Oh yeah, NX, NY, and Z, you mean?
Yeah, whole thing squared, maybe, right?
Interesting.
Because I assume some of the Z2s are flipping the sign of NX, NY, and NC. Oh, I see. Maybe they flip pairs of them.
Yeah, we have two pi rotations, so they flip pairs of them, and then there's if we include the crystal symmetry, that kind of cyclically permutes NX, NY, and Z. So I think the product of the three sounds good.
Yeah, anyway, maybe that's a discussion for a different time. Any other questions? All right, if not, thanks a lot, Nat. That was very nice, very clear. And I don't think we would have heard about SSE in any other context. It's like this black box, right? So it was good to hear that, and along with the SPT stuff. So it's pretty complicated. I realize now that you explain it. It's not something you can turn the crank for every new model, right? You've got to set it up.
Yeah, you have to find a model that you can actually simulate. Otherwise, you have to use some other techniques. It's very like model dependent.
Yeah.
I guess you can definitely do it. Is just it might be slow. So these are sort of already for certain problems you can make it faster.
Correct. All right. So thanks again, and have a good Friday, everyone. Talk to you soon.
Thanks, Nat.
Oh.
Thanks, Nat.
Thanks. Thanks.